Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Welcome back, everyone. I am P.S. Chatterjee, and you are watching Structural Design Only, a channel with a different vision. This space isn't just for civil and structural engineers, it is also for the innovators in the Excel community who believe our spreadsheets should be doing the heavy lifting. Today, we are going deep. We are launching a brand new series, Stepped Column Design for Truss with Crane, Theory and Excel Automation, strictly following IS 800. 2007. In this first part, we'll lay the foundation. I'll be breaking down the core engineering theory and the complex calculations behind stepped columns through a detailed presentation. I hope you are going to enjoy the video and you will find it helpful for your professional journey. If you do, please like, share, and subscribe to the channel, and don't forget to leave a comment below. I'd love to hear your thoughts on this design approach. If you'd like to support my efforts and the development of these tools, you can find my payment link in the description. Your support helps me keep creating high-quality content for our engineering community. Let's move to the next slide to visualize the geometry and the various sections that build this formation in both 2D and 3D. Slide title: Visualizing the Stepped Column, Breakdown of 3D and 2D Profiles. The use of this type of combination column is a standard and highly popular choice for industrial sheds equipped with crane systems. In this slide, we are going to dissect the column assembly. Looking at the screen, we start with the foundation or footing for the column. To build this system, we typically use two identical I-sections placed parallel to each other. In the bottom portion, you can see the two channels placed back to back. On the right-hand side, we have the corresponding cross-section for this lower assembly to show how the mass is distributed. Moving to the upper section, look closely at this projected portion or the bracket. This is where we will place our gantry girder. Because this girder is seated on the projection, the crane load is applied at a distance from the column's vertical axis. Since it is shifted away from the center, it will develop eccentric loading for the column system, a critical factor we must account for in our design calculations and Excel automation. Now, look at the upper column member supporting the truss. To integrate this member into our system, we provide an ISMB section to serve as the critical connection interface with the main column assembly. Since we are designing for a roof truss with a crane system, the orientation of this column is aligned along the span of the truss. We must position it precisely so that it aligns closely with the web of the rear I-section. Notice a key design feature here: we do not need to extend this specific upper column all the way down to the foundation level. Instead, we utilize the vertical load from this truss column as a strategic countermeasure. By positioning it on the opposite side of the neutral axis, the gravity load from the roof helps neutralize the eccentric moment generated by the crane. This creates a more balanced and efficient load path, reducing the net moment for the entire column system. Now, on the screen, we see the gantry girder complete with the crane rail. This entire assembly must be positioned precisely over the top projected portion of the column, also known as the bracket. Once this arrangement is seated, the integrated system looks like this. We have now successfully completed the structural assembly of a stepped column designed for a roof truss with an active crane system. With the physical configuration clear, let's move to the next slide to dive deeper into the theoretical analysis. Now, let's look at the classification of loads on our stepped column. To keep our Excel automation organized, we categorize these into 4 primary groups: dead, live, crane, and wind loads. Notice the subscripts. We use specific labels like TR for truss and CR for crane to ensure there is no confusion during calculation. A key point here is the horizontal crane load WCR, H. This represents the surge and drag forces that create lateral moments. By organizing our inputs this way, we can precisely calculate how the vertical truss load acts as a counterweight to the eccentric crane moments. Title of this slide is Component Breakdown Dead Load. The component breakdown of the total dead load, or P_DL, at the column base. First, we define our geometry. We have S for span and B for bay length or spacing. Our roof slope, theta. For most of our industrial designs, we use a 1 in 3 slope, which is approximately 18.43 degrees. And we also consider h, the height of our column. Now, let's look at the truss weight. Based on our SP38 data, I've developed a linear coefficient to simplify your automation. By using the formula 0.383 times S, you get a realistic unit weight in kg/m superscript 2 that accounts for the increased steel consumption in larger spans, especially critical for crane integrated columns. Covering materials. Next, we add our covers. For standard 0.5 mm galvalume or CGI sheets, we consider around 7 kg per square meter, and for our purlins and girts, we take 6 kg per square meter. Note that these materials lie directly on the slope, which is why that 1 in 3 ratio is so important. Finally, we reach our derived formula. Notice how we calculate the tributary area as S multiplied by B, divided by 2. Crucially, the truss weight stays outside the slope factor because it's already based on the plan area. However, we divide our sheeting and purlin weights by cos theta to account for the actual rafter length. We then add our side cladding and the self-weight of the column. This formula is the engine behind the Excel automation tool we are building. By accurately breaking down these components, you ensure your column bases are designed for safety, longevity, and industrial-grade performance. Let's see how to plug this into our Excel script. Let's move to the next slide for more calculation. Title of this slide is live load on a sloping roof as per IS 875 Part 2. Moving on to live loads, we follow IS 875 Part 2. For any industrial roof with a slope up to 10 degrees, the code mandates a standard base live load of 0.75 kN per square meter. However, as our roof becomes steeper, the probability of human access or significant accumulation decreases. Therefore, the code allows a reduction. For every degree increase beyond 10 degrees, we reduce the load by 0.02 kN per square meter. But there is a limit to this reduction. To ensure structural integrity, the live load value can never fall below a minimum of 0.40 kN per square meter, regardless of how steep the slope is. For our specific design where the slope angle theta is greater than 10 degrees, we use this master formula: live load equals 0.75 minus 0.02 times the excess angle. In our case with a 18.43 degree slope, this calculation provides the precise intensity needed for our column base analysis. Let's move to the next slide. Title of the slide is Wind Load Calculation based on IS 875 Part 3. Now, looking at our finalized wind load calculation, we have a complete system for automation. By using our Table 03, you can instantly find the design wind area multiplier for any common shed configuration. Formula for this multiplier: MUL equals to span multiplied by bay, whole divided by 2 cos theta. Finally, the total wind load WL total equals to MUL multiplied by zone pressure. In this application we have 3 pressure zone: 100, 150 and 200 kilograms per square meters. For example, a 30 m span with a 6 m bay length and slope 1/3 gives us a plan area multiplier of 94.87 square meters. Simply multiply this by your local zone pressure to find the base wind load, that wind load, which we will then use for our final pressure coefficient analysis. As you can see in the diagram, this total load is perpendicular to the roof surface and acts upward. To design our stepped columns, we must resolve this into 2 components. The vertical component, WLV, calculated using cos theta, creates axial tension or uplift. The horizontal component, WLH, calculated using sin theta, works alongside your crane's horizontal surge to create the critical shear force and bending moment at the column base. This combined additive case is the worst case scenario we must design for to ensure maximum safety. Let's move to the next slide for more explanation. Title of this slide is Wind Load on Side Walls based on IS 875 Part 3. Now that we have mastered the roof, let's look at the horizontal cladding on the side walls. To calculate this load, we use the same zone pressure we established earlier, but our multiplier logic changes. As you can see in the diagram, the tributary area for our side wall is simply the base spacing multiplied by the vertical height of the cladding section. Because the wall is vertical, the entire force acts horizontally. Say this load is WLH1. Then, total horizontal load on column base, WLH total equals to WLH plus WLH1. This creates a lateral bending moment in our columns that must be added to the horizontal wind load from the roof and the crane surge we calculated earlier. In our Excel tool, we will automate these wall loads to ensure your column design accounts for this cumulative lateral thrust. Let's move to the next slide for more explanation. Title of this slide is, Load Application Points and Moments. Here, we are looking at the side elevation of our stepped column. This system is a built-up assembly of two I-sections. The top portion serves as the truss column, and the bottom portion is the reinforced stepped section. To design this effectively, we define several key parameters. The total height of the column is capital H. The height of the upper truss column is small h, while the depth of the column nested within the stepped section is denoted as h1. The gap between the two main I-sections is small letter a. To simplify our analysis, we have divided the entire system into two equal halves, shown here as h by 2. Now, let's identify the forces. The yellow downward arrow represents our live load, PLL, the red arrow is our dead load, PDL, and the green upward arrow is the vertical wind load, WLV. These loads pass through the center of the top column. Notice that their distance from the center line of the stepped column is eccentricity E1. Next, we have the maximum vertical crane load, PCR, acting at an eccentricity of ECR from the stepped column's center line. The yellow horizontal arrow at the rail level is our crane surge load, PCRH. Finally, our total horizontal wind load, WLH, is shown passing through the center of the total height. With these application points clearly defined, we can now calculate the exact bending moments acting on the stepped column. Now, let's look at our first design condition, dead load, live load, and crane load. In our Excel tool, we first sum our vertical gravity loads to find W1. Multiplying W1 by our eccentricity E1 gives us our primary moment, M1. We then account for the vertical crane moment and the horizontal surge moment, MCR2, which acts over the calculated height of the step. Summing these gives us our total design moment for this case, MDL and LL. Now, let's switch to the dead load, wind load, and crane load condition. Notice the magic in the logic here. Because wind acts as suction, our net vertical load W2 is the dead load minus the vertical wind uplift. Say moment due to W2 is M2, then M2 equals to W2 multiplied by E1. This can significantly change your eccentricity moments. Additionally, we now introduce M3, the moment caused by the total horizontal wind pressure acting at the mid-height of our column. M3 equals to horizontal wind load, WLH, multiplied by H divided by 2. We already calculated the moments due to crane load, MCR1 and MCR2. Say, MCR1 plus MCR2 equals to MCR. Therefore, total moment due to dead load, wind load, and crane load, equals to M2 plus M3 plus MCR. By automating these swaps in Excel, we can instantly compare both cases to find the absolute worst case for our design. Let's move to the next slide for more calculation. Name of this slide is Sectional Properties of the Column Combination. After finalizing the assembly, we must calculate the mechanical properties of this specific section to proceed with our design as per IS 800-2007. First, let us look at the individual section properties shown on the left. For each I section, we identify the cross-sectional area as AX. We also establish the center-to-center distance of the CG, and the individual moments of inertia, denoted as IXX and IYY. Now, look at the 2D diagram. We have two I sections placed at a clear distance, A. The total width of each flange is F, and the total depth is D. The global y-axis passes exactly through the center of the combination. Therefore, the distance from the individual CG to the global y-axis is denoted as R suffix y. Let's calculate the combined properties. The total cross-sectional area is simply 2 times A suffix x. Since both sections share the same horizontal neutral axis, the distance R suffix x is 0. Consequently, the combined moment of inertia about the x-axis, IXX, B, is simply 2 times IXX. For the y-axis, we apply the parallel axis theorem. The combined moment of inertia, IYY, B, is 2 times the sum of the individual inertia and the area multiplied by the square of the distance, RY. Finally, we determine the section modulus. ZXX, B is the combined inertia divided by the extreme fiber distance y. Similarly, ZYY, B is calculated by dividing the combined y-axis inertia by the distance x. These values are the backbone of our Excel automation. Let's move to the next slide for more explanation. Name of this slide is Dimension Calculation for Plastic Properties. Now that we understand the general layout, let us dive into the specific mathematical derivations required for our Excel automation logic. First, let us define our reference dimensions shown in the bottom left. Along the x-axis, the eccentricity Rx is 0. The vertical extreme fiber distance y is simply d divided by 2. For the y-axis, the distance from the global center to the individual CG, Ry, is f plus a, divided by 2. Finally, the horizontal extreme fiber distance x is calculated as f plus a, over 2. Now, look at the derivation for the x-axis properties. As established, the combined moment of inertia is 2 times Ixx. To find the section modulus, Zxx com b, we divide the combined inertia by the distance d over 2. This simplifies to the final formula, 4 times Ixx divided by d. Next, we move to the y-axis using the parallel axis theorem. The combined inertia, Iyy com b, is calculated as 2 times the sum of the individual inertia and the area multiplied by the square of the distance a, plus f over 2. Squaring this distance is critical for engineering accuracy. Finally, we derive Zyy com b. By dividing our combined y-axis inertia by the extreme fiber distance, and simplifying the algebraic expression, we arrive at our master formula, 4 times Iyy, divided by a plus f, plus the area multiplied by the sum of a and f. Using this simplified equation in your Excel sheet will make your design tool faster and more efficient. Let's move to the next slide for more explanation. Now, we move to the final summary of our structural forces. This table is the heart of our automation tool, where every load we have calculated so far, from dead loads and wind uplift to crane surge, is consolidated into 2 critical design cases. First, look at load case 201. This is our primary gravity case using a factor of 1.5. Here, the vertical load Pu1 combines the truss and column dead loads with the live load and the maximum crane wheel load. Our horizontal force Hu1 accounts for the crane surge. And the moment M_Uy1 handles the eccentricity of that crane load relative to our stepped column height. Next, we evaluate load case 202, using a factor of 1.2. This is a more complex scenario where we introduce wind forces. Notice that for the vertical load Pu2, we subtract the wind uplift WLV, because it lightens the total gravity load on the column base. Hu2 is the horizontal load due to wind and horizontal surge load from crane load. The moment MUI2 now integrates the powerful effect of the total horizontal wind pressure acting at half the column height, combined with our crane eccentricity. Secondary moment calculation along the x-axis. But here is the magic reveal for professional engineering. In a real-world project, no column is perfectly straight, and no load is perfectly centered. To account for construction tolerances and accidental eccentricity, we introduce a by multiplying our total vertical loads, Pu1 and Pu2, by a factor of 20 divided by 1000, representing a 20 mm accidental shift. We derive Mux. This gives us the final values needed for our biaxial interaction check. Even if your theoretical model shows zero moment on the major axis, this small addition ensures your design is safe, robust, and fully compliant with professional standards. Let's move to the next slide. Title of this slide is Calculation for Factored Allowable Stresses. Once we have determined our design forces, we must calculate the allowable stresses for our stepped column. We begin by defining the physical height of the stepped portion, HST. Here, HST is the height of the stepped column. To find the effective height, we apply the buckling coefficients. For the major axis, Kx is 1.50, resulting in a larger effective length, Lx equals to 1.50 multiplied by HST. For the minor axis, Ky is 0.75, giving us a smaller effective length, Ly equals to 0.75 multiplied by HST, due to the lateral support from side girts. For our material limits, we set the allowable bending, tensile, and shear stresses equal to the yield strength, Fy. These values represent the plastic capacity of the steel before we consider the effects of buckling stability. Next, we determine the critical elastic stresses in compression for both axes. By integrating our effective lengths with the radius of gyration, r, we derive FCCx and FCCy. These are known as critical elastic stress in compression. Notice that the radius of gyration is squared in the numerator, accurately reflecting Euler's buckling theory for our built-up section. Finally, we calculate the allowable compressive stresses using the Merchant-Rankine interaction formulas. These equations are essential as they bridge the gap between theoretical elastic buckling and actual plastic yielding. As per the technical logic of IS 800, we use an interaction exponent, n, of 1.40. This specific value accounts for the inherent imperfections in our built-up steel section, such as initial crookedness or residual stresses, ensuring a safe and compliant design. Our automation tool will automatically identify the minimum of these two values, sigma ACX and sigma ACY, to use as the final design compressive strength in our safety check. With these allowable stresses finalized, we can now proceed to the biaxial interaction check to confirm if our column is safe under the combined effects of axial load and moments. We have now arrived at the most critical stage of our structural analysis, the biaxial interaction of axial load and moments. In professional practice, a column never faces just one force in isolation. To ensure total stability, we must verify that the combined effect of vertical compression and multidirectional bending does not exceed the section's total capacity. Look at the central equation. For our design to be safe, the sum of three ratios must be less than or equal to 1.00. This linear interaction formula, derived from Indian Standard 800, combines our axial load ratio with our major and minor axis bending ratios. The first term, Pu over Pd, compares our factored axial load to the design compressive strength. The second term, Mux over Mdx, handles the moments about the major x-axis, including the accidental eccentricity we calculated. Finally, Mui over Mdy accounts for the moments about the minor y-axis, which are primarily driven by crane eccentricity and wind loads. In our automation tool, This equation acts as the final gatekeeper. By pulling in the factored moments and the allowable stresses we derived earlier, the tool calculates this total sum instantaneously. If the value is 0.95, your column is safe and efficient. If it exceeds 1.00, the section will fail under combined stress, and you must refine your design. This concludes our structural journey for the stepped gantry column. By integrating wind, gravity, and accidental forces into this final biaxial check, we ensure a design that is not just theoretically correct, but practically robust and fully compliant with Indian standards. Use this automated logic to build faster, safer, and more professional structures. Thank you so much for watching this deep dive into the design logic of stepped gantry columns. We have covered everything from consolidated factored loads to the critical application of accidental eccentricity. But as an engineer, the real power lies in turning this complex theory into a fast, error-free tool. In our next masterclass, titled Stepped Column Design, Theory and Excel Automation, IS 800-2007, Part 02, we will bring all these formulas to life. I will show you how to build the automated dashboard that handles these biaxial checks with a single click. If you found this session helpful, please hit the like button and subscribe to our channel, Structural Design Only. Don't forget to turn on the notification bell so you don't miss the release of Part 02. If you have any technical doubts about today's calculations or the Merchant-Rankin formula, please drop a comment below. I personally review every question to help you grow as an engineer. Stay tuned, keep designing, and I will see you in the next session.